Hello everyone, in this video let us study about source transformation technique in more detail. So in my previous video I have explained you about the source transformation, that is converting the practical voltage source to the practical current source to the practical voltage source. So the question here is, can we apply this source transformation technique to the ideal sources? So you know about the ideal sources, right? So this is ideal voltage source. This is ideal current source. That means it will not have any resistance. That is, voltage source has no resistance in series with it and current source has no resistance in parallel with it. So these are the ideal voltage and the current sources. So can I convert this to this or this to this? Can I convert? The question is this one. Can I convert ideal voltage source to the ideal current source or ideal current source to the ideal voltage source? So the answer is no. You can't convert, because see, you know this is a practical voltage source, right, which has resistance in series with it. So to get the ideal voltage source, what should be the modification done to this source? So this will be R equal to 0. That means it will be shorted. So when it is shorted, I'll get the ideal voltage source, right? So to convert the practical current source, that is which is having the resistance in parallel with it, to convert this to the ideal current source, so what is the modification that should be done? So here it should be R equal to infinite. So when R equal to infinite, that means it is offering very high resistance. So this becomes open. When this is open, you are left only with the ideal current source. So now if I want to convert, here what we did, it is V and we had resistance R. So I was equal to V divided by R. So when there was a resistance, I equal to V by R. So in this case now, what is R? R equal to 0. So V divided by 0. So something divided by 0 is undefined. We will say it as infinity, but actually it is undefined, right? So we can say that the ideal voltage source cannot be converted to the ideal current source. Similarly, we have this one. So to convert this to the practical voltage source, we had V is equal to I into R. I into R. In this case, R equal to infinity. Okay, voltage I into infinity. So this is also not possible. So we cannot convert ideal voltage source to the ideal current source or ideal current source to the ideal voltage source. So that's not possible. So let us next consider dependent sources. So can we apply the source transformation technique to the dependent sources? So you know, dependent sources means they do not have fixed value like independent sources. So whatever we just consider, it will be having fixed value. Independent sources like voltage source of 15 volts, current source of 15 amperes. So the value is fixed. But in case of dependent sources, the value is not fixed, but it depends upon the other circuit current or the voltage, right? So you have seen different types of dependent sources like voltage dependent voltage source, voltage dependent current source, current dependent voltage source, current dependent current source. So these are the 4 different types of dependent sources where it is depending upon the circuit current or the voltage. So if I consider a dependent source, okay, so if I consider this one KVX, so this is the voltage dependent voltage source. So this can be converted to current source. Yes, we can also apply this concept of source transformation to the dependent sources also. So this one, what it will happen, we will be getting the dependent current source now, and what will be the value? It will be KVX divided by R. Okay, then we will be having resistance R. Okay, so we can convert the dependent sources also. So source transformation is possible in this case. Okay, just make sure that the controlling variable should not be altered in this case. Okay, controlling variable, you should take care of the controlling variable. And remember, this source transformation technique, the resistance value doesn't change. R value doesn't change, right? See, here it was R, here also it is R. Okay, and second thing, is you must remember that the source transformation technique is based on the concept of equivalence. Equivalence. That means, okay, this terminal characteristics, okay, that won't be changed. Terminal characteristics won't be changed. For example, if I consider 10 volts, 2 ohm, okay, and I will have a load resistor RL, okay, that is equal to 1 ohm, or let me consider it as 3 ohms. 3 ohms. So now I will convert this to current source. Okay, so this is 10 divided by 2, 5 ampere, and here we will get the same resistance in parallel, and here we have 3 ohm load resistor. Okay, so what was the current which is flowing through this load resistor? So we can say 10 divided by 5, that was 2 amperes. Okay, if I consider this as terminals, 2 ampere, and the voltage here across this will be 6 volts. Okay, now we can see what is the current. You can use the current divider rule. 5 into 2 divided by 2 plus 3, 5, 2 amperes. See, this is the same terminals now, A and B. The current which is flowing through that also is 2 amperes, and the voltage also can be considered as 6 volts. So 2 ampere 6 volts, 2 ampere 6 volts. So the terminal characteristics are unchanged even though you are performing the source transformation. Okay, so the terminal characteristics will be same. Same. Okay, so now if I enclose this, okay, if I enclose this in a container, okay, this in an container means I don't know whether there is a voltage source or the current source. Okay, so here also it is 2 ampere, here also it is 2 ampere. So we cannot identify here, right? If it is placed in a container, we cannot identify the type of source. Okay, we cannot make the difference now. I can't imagine, like I can't tell it confirmly that whether the voltage source is present here or the current source, because the terminal characteristics is same. Okay, terminal characteristics is same. So the source transformation cannot be applied to ideal sources. It can be applied to practical sources. It can be applied to practical sources. It can be applied to the dependent sources also. It is based on the concept of equivalence. And remember, the voltage source or the current source, okay, and its equivalent, voltage source or the current source and its equivalent, it establishes current in same direction. Establishes current in same direction. So just now we saw a voltage source, and here we had RL. There was 2 ampere, and here I replaced it with the current source. Here there was RL, and here also it was 2 ampere. So this was voltage source which was establishing the current of 2 ampere in the downward direction, and this was its equivalent which also established a 2 ampere current that is in the downward direction. So that is what this means. Okay, so this is all about the source transformation. We will also solve one question that is based on the source transformation where the dependent source is being involved. Okay, so this is that question where we have to find the value of Ix. Okay, value of Ix using the source transformation. See, since you are going to find this Ix, which is nothing but the current which is flowing through the 10 ohm resistor, make sure that you are not going to alter that part. Okay, you are not going to alter this part. So don't apply the source transformation technique to this particular current source, but apply the source transformation to this part, that is the dependent source. So this is a current dependent, right? Current dependent voltage source. This is the voltage source, and the controlling variable is current. So it is current dependent voltage source. So if you are having a current source something like this, the internally what happens, the current direction should be, okay, that is towards the positive terminal. That is, the arrow should be directed towards the positive terminal. So here it should be directed towards the positive terminal. So the current direction will be something like this. Okay, so now I will redraw the circuit. I will write it in terms of ampere, okay, for simplification purpose, that is 0.024 amperes. Then we have 10 ohms, and here we have a resistor now which is in parallel, because I am going to convert this dependent voltage source, that is, to the dependent current source. So here I told you about the direction already. So this is downwards. And what will be the value? You know, it will be voltage divided by the resistance value. So this is 2Ix, and here it will be 5. So now these are the current sources. Though it is dependent and this is independent, I will write an equivalent to this. Okay, so that will be 0.024 minus 2Ix divided by 5. Okay, so I will write like this. Next, I will write 10 ohm, and here I am writing 5 ohms. So I want this Ix value. So now I can apply the current divider rule, right? That is 0.024 minus 2Ix divided by 5 into 5. Okay, this is inside bracket. So total resistance is 15. So this is 15Ix. I am cross multiplying it. And here it is 0.024 into 5. So this is 0.024 into 5. So we can write this as 24 divided by 1000 into 5 minus 2Ix. Okay, because 5 gets cancelled here. So this comes here 17Ix. That is equal to, okay, 24 divided by 200. And here after simplifying, you are going to get 7.059 milliampere. Okay, so this is the value of Ix.